is about will be the 7th series of the AP MTT EMC webinar, and this is basically the second industry speaker that has been invited lah, okay, to our webinar. Okay, so basically I would say that today is very grateful for us to have Mr. Anwar, okay, to give to share what has been doing at this moment, because he is from RNS and he is actually involving with the reality, the current problem statement for us. You know, sometimes when we actually doing or exploring on research works, okay, so this is a good prospect for us to solve a real world a reality problem statements. Okay, so hope we actually can we can actually gain lots of knowledge from today's talk. Okay, so basically talk for today is about resolving the interference of 5G base stations toward the satellite service to achieve harmonious coexistence in the C-band. So we know that the Malaysian government is hoping to somehow implement a 5G technology in Malaysia, maybe in the next 2 or 3 years. So Mr. Anwar will share about it later on. So before we start, let me read the speaker biography. Okay, Mr. Anwar is with RNS. He's holding MSc Electrical and Electronic Engineering from USM. So his experience include 18 years of experience in wireless communication and mobile network testings. Okay, he is a senior IEEE member and committee for IEEE MTT EDSSSC Penang chapter. Okay, so this one, Malaysia 5G Task Force Group member, chairman of 5G Ecosystems and Timeline Sub-Working Group under the Spectrum. Under Spectrum Working Group. He's also the vice chairman of MTSFB IMT and Future Network Working Group, chairman and main author of MTFSB 202RO Technical Code Documentation, which is referred to the technical specification for IMT 2020 5G systems. He's also one of the author for another technical code prediction and measurement of EMF exposure from solar base stations. I think there is a very long biography that I've read. So without further delay, you can actually start your talk, Mr. Anwar, please.
Okay. Everyone can see my screen?
Yes, I can see now.
Okay. Right. So thank you very much, Prof. Fauzia. And also thank you everyone for joining this session. Good afternoon. Assalamualaikum. My name is Anwar from Rohde & Schwartz. So today I'll be presenting actually a critical topic, which is the issue of coexisting the 5G base station and also the incumbent satellite service in the C-band. As everyone know that there have changes in the policy for 5G in Malaysia, right, from the past 2 years up to today, right. As far as I know, even with the current setup, right, with the special purpose vehicle and also single hosted network deployment of 5G, as far as I know, the issue of interference in the C-band has not been fully resolved yet. Right. So this is like Prof. Fauzia said, this is a real life issue, right? Something that prevent not just us but many countries from deploying a proper 5G service. Okay, so without further ado, let me proceed with the presentation. Okay, I think Prof. Fauzia has explained about my profile, so I will skip that. So the objective of today's presentation is first to understand the importance of this 3.5 gigahertz band for 5G, right? and also the importance of this band, C-band, for satellite service. So both services need the access for the bandwidth in this range, 3.4 to 4.2 gigahertz, the C-band range, right? For 5G, maybe 100 to 400 megahertz of requirement to, to offer a good service for 5G to the users, to the public. Then we want to analyze the possible interference from 5G signal towards the satellite service receiver. What is the interference source, right? And what causes this interference? Then we want to discuss, I think this is much related to the participant here, mostly lecturers, professors from university, right? Maybe we can get into deep on this mitigation technique that can be deployed or need to be deployed to reduce the interference. We will go first with the lab demonstration, right, to simulate the coordinating scenario. And the reason we want to do the lab simulation first is that we want to get the limit of the mitigation that is required. And basically, in our case, it's a bandpass filter. Right? What is the roll off of the bandpass filter, right? The band stop that is sufficient to prevent the 5G interference towards the satellite service, right? Then we will go for the theoretical calculation before we go for the field test scenarios. And we actually done a field test in UTM KL together with the MCMC, the operator, the satellite service provider, network vendors. So, but it's not really 100% conclusive from the test yet because we don't have much time on doing the test the other day. But anyway, let's move on. Okay, why is C-band important for both 5G and the satellite service? So for 5G, right, the C-band frequency is commonly known as 5G 3.5 gigahertz. It ranges from 3.3 to 3.8 gigahertz range, and this is based on 3GPP specification for N78 band. Right? So this 3.5 gigahertz range is ideal for early deployment of 5G because it has both the propagation characteristic and potential of large bandwidth, right? So it can provide both capacity due to large bandwidth and also coverage because it is the propagation characteristic is somewhat comparable to the LTE at 2.6 gigahertz, for example, right? So you have both of this feature that you need for 5G, right? So for 5G, when we want to deploy the service, right, it has to cover the enhanced mobile broadband service first, right? So we need the service to be able to deliver peak download speed of 10 to 20 gigabit per second and a reliable 100 megabit per second user experience in urban areas, latency 1 to 4 millisecond, apart from the other parameters that is required for eMBPS, right? So to achieve this, right, it is very important that the 5G service have access to the 3.5 gigahertz, right? To have at least 80 to 100 megahertz per operator or per services to enable the 5G so-called performance to the user. And lastly, right, for 5G, in terms of the worldwide 5G ecosystem, the 3.5 gigahertz is one of the most used equipment and base stations, has most user equipment and base station support, right? Based on the GSA report and the GSMA report, right? So, for example, when we want to buy Samsung S21 5G, for example, right, it covers this frequency. It may not cover the other frequency, but this frequency, I would say 90% or almost 100% of the user equipment will cover it for the use of 5G, right? Maybe a small percentage only that does not have this frequency. So it is very important for the 5G ecosystem as well. Okay. But who are the current user of this C-band, right? So the current use of C-band, it depends on countries, but the main use is as a fixed satellite service, right? Especially in Malaysia. The fixed satellite service, or FSS, in the C-band includes large satellite earth station, which serve as a gateway that carry trunk or network traffic, right, to and from the satellite space station. It will also be used as a TTNC, telemetry, tracking, and command station used for communication between spacecraft and ground. So this is where the Earth station sending control to the satellite, right? In terms of to maintain the position and the critical control signal. Okay. And importantly, in especially in Malaysia and Southeast Asia, the C-band is being used as a VSAT, which is a small two-way satellite system primarily used by business, but also for military and government application. Right? So this VSAT is the main user, especially in Southeast Asia. Right? Some countries like Hong Kong, they use the C-band as a satellite master antenna television, where the system use multiple satellite and broadcast signal to create a single integrated cable signal for distributing a cable TV network. So basically, you have a very tall building, right? You have like those condos or apartment in Hong Kong, then they have the satellite dish at the top of the building, so they receive the broadcast signal from the satellite and distribute it to the units in the building, right? So these are the current users of C-band. Okay. And you can see why C-band is still important for the satellite service is that there are currently about 16 or more number of indigenous C-band satellite system, right, in space. And apart from that, there are more than 80 geo C-band satellites serving in Asia, and more than 3,800 TV channel are being distributed by C-band. And in 2018 alone, the revenue for the broadcast service in the C-band is about 56 billion US dollars, right? So it's pretty much an important service for the satellite service provider in the usage of the C-band, and we are talking about 56 billion in Asia Pacific alone, not the whole world. So we talk why some countries can have 5G, right? For example, Korea, Australia, and why some countries are still, having problem in deployment. This is because in the country that located at the equatorial circumference of the Earth, we are prone to high volume of rain. So the satellite service cannot simply choose a band that susceptible to rain attenuation. So C-band is immune for this rain attenuation. That's why the satellite service prefer to use this C-band for their critical signal transmission, right? If you can see here, right, countries like North Asia and Australia, New Zealand, these are low-risk countries because they don't have C-band broadcast service anymore, easily to migrate, and can fully focus on 5G at the 3.5. In some countries, like for example, in the South Asia, like India and Pakistan, there is still usage of satellite service at C-band, but on a smaller scale, right? We can go for ad hoc adjustment on the antenna configuration, I believe, to solve this. Right? But there is still a risk there. However, the highest risk will be the Southeast Asia up to the Pacific countries, Papua New Guinea, Indonesia, especially big countries, and up to Taiwan and Hong Kong. So these are in the so-called equatorial region, right, where we have a high volume of rain, and it's hard to move the satellite service from C-band to the other band, right? So how do we do this, right, to mitigate the issue of the interference? So first, before that, we want to know who caused the interference and how, right? So the challenge in deploying 5G is because when we want to deploy the 5G base station adjacent to the satellite service receiver, right? The 5G signal is expected to give an interference at the satellite Earth station. For example, look at here, we have a satellite, and this is downlink, right? So the signal from space is very weak once it reaches the Earth because it's very far away, right? So this is a Earth station receiving the signal, right? Very weak signal, and we have a 5G base station nearby, right? Very high signal up to 200 watt of RF power, right? Then this is a UE, right? Receiving. Then is there is some unwanted signal that can be received by the antenna of the Earth station here that can cause the system to be corrupted, the signal to be corrupted, right? So these are the interference scenario from 5G base station to the FSS terminal. Right? So there are two main, specifically speaking, there are two main interference that we are talking here. First is the satellite service receiver blocking due to saturation caused by high-level 5G signal. Let's say you have a 5G base station here, and you have the satellite service receiver, right? Then 5G is sending a signal across the area, and the LNB is still receiving the unwanted signal, right? And high out of band signal from the 5G base station, which cause the LNB to be saturated and making the satellite service signal to be distorted. Right? So why is this happening in the satellite service receiver? Okay, this is because, right, the satellite service receiver consists of the antenna, right, connected to a feed horn and then to the LNB. And LNB is a low noise block. It consists of LNA, low noise amplifier, and with a mixer. Right, so the signal coming in here at C band, and when it come out from here, it's called IF, intermediate frequency, and it's about 950 to 1.7 gigahertz. Right, so coming 3.4 to 4.2, come out around 1.4 to 1.5 gigahertz of signal. Right, so basically, right, the high the LNB has a very high gain. Because remember, the signal from the satellite is weak when it reaches the Earth station antenna. So you need a very high gain LNB, right, so that you can boost up the signal. Okay, but this LNB is meant to amplify a weak signal. But if a 5G signal of 46 dBm or 49 dBm being transmitted near the satellite antenna, right, then it will cause the saturation. Right? For example, here is the input power that coming in from here. This is the output power, right? In theory, it will be straight line here, the M here, right? But this is a gain, right? But in practice, there will be a saturation point where if the input power is high enough, it will saturate the signal. So the output power will no longer as expected. So this is what happened when we have this 5G signal still being detected by the LNB, still being picked up by LNB. Right? So this is the blocking issue. We call it the receiver blocking issue. Right? The other issue will be the out of band emission, where this is coming from the base station out of band emission that can so-called go into the frequency range of the satellite service. Right? You have an adjacent 5G signal, and you may have an spurious emission that, when it received again by the satellite receiver, right, it will be amplified. Then when it amplified, it can be a so-called spurious interference to the decoder. But most of my study here will be on the receiver blocking. The reason is that we are taking the requirement from TGBP, right, that says that for 5G base station, the spurious emission level should be below minus 52 dBm per megahertz. Right, so this is to prevent this scenario. So the network equipment provider like Huawei, Ericsson, Samsung, ZTE, Nokia, they have to comply to this standard. Right? Then we shouldn't be seeing this out of band emission. But of course, it's best to measure it. But based on my previous study, I only looking for the so-called the receiver blocking. Let's focus on that. So the mitigation technique that we can do, right? This is based on reference and study and from the technical papers, right? The first mitigation that we can do is to have a guard band between adjacent system, meaning that if you have 5G and satellite service together, you need to have a separation, right? So this is the first interference mitigation that we can use. The second is to add a bandpass filter at the satellite receiver. This is to help in the receiver blocking, right? Okay. And there are other mitigation technique. For example, you can expand the distance between the interference source and the interfered victim. Means that you increase the distance, the physical distance between the two antenna. But this is not feasible if you need to have good coverage around the area. But maybe in one or two places you can do it. But in Malaysia, the satellite service receiver is ubiquitous, means that it's everywhere, right? It can be everywhere. So this is not really a so-called a good setup. Only for a few cases of ad hoc mitigation we can use for this. The next one will be to optimize the 5G base station to reduce the antenna gain in the interference direction. Again, this is for case-by-case basis, right? One or two cases that we can apply to this, not all, not for mass deployment. Improve the spurious emission indicator in the 5G base station. Again, this is for the spurious emission mitigation. This is expected from all the 5G base station provider, right? Reduce or optimize the transmit power of the 5G base station. Again, in this case, it's case by case, right? Or add a physical isolation. For example, you can put a caging, but the problem with caging is that you can only put it behind the 5G, behind the satellite service antenna. You cannot put it at the front. Okay, put the front, then the signal from satellite also will be blocked, right? And so you have only one direction to put the caging, and also it is gain case by case. So the only mitigation technique that can do for all mass cases will be by adding the guard band as well as the band pass filter. So we can model it for all cases in theory. Right. So what is the plan for C-band? So the plan for C-band is to do a frequency segregation, right, in a coexistence scenario, where we will take some frequency bandwidth from C-band to award it to 5G. The rest remain to the satellite service. However, we need to have the guard band. Remember, because of this is one of the mitigation techniques required, right? So the question is, what is the size of the guard band? And then for this, the answer is depend on the bandpass filter specification in the market, right? Can we do a custom design that can have a very narrow so-called roll-off to have a smaller guard band, right? So this is the existing allocation in C-band, and this is the proposed allocation. So we are starting the 5G from 3.4 to a frequency, unknown frequency, right? We don't know, 3.6, 3.7, right? It's not yet fixed, right? And then we have a guard band range. Again, it's not a fixed value at the moment, depending on few criteria or factors. And the rest will remain as satellite service up to 4.2. So this is the part where we need to identify. It's not yet identified at the moment. Right. So to understand the way to reduce the gut band, for us to first learn about the bandpass filter, right? So the bandpass filter can help to determine the size of the gut band as well as for the receiver blocking issue, right? So it is deployed together. The bandpass filter deployed together with the gut band as mitigation technique to enable coexistence between 5G and the satellite service, right? The BPF characteristic or the performance will determine the size of the gut band required for the coexistence. Right? So the important parameter here, we need the insertion loss to be very low at the pass band, right? So that we don't want to, the signal from the satellite is very low already, right? We don't want to add another lossy band pass filter to reduce it. So it has to be very good insertion loss at the pass band, right? Suppression at out of band rejection frequency means that this is where you want to have the rejection, right? So we are looking at more than 45 dB stop band range, stop band specification at 3.6, right? And also at the 4.3, at both end of the pass band. Right? So this is a band pass filter. Return loss, as standard, we want it to be more than 10 dB, right? An important thing here, and this is what a lot of people overlook, is the group delay, right? The group delay is very important because if we are transmitting or receiving signal, a broadcast signal, video signal, then it's okay because the modulation of the signal is about 8 bpsk or even lower than that, right? 4 bpsk, for example. But for data transmission, for example, in Malaysia, we have business usage, right? It's used for business, so we may need to transmit data. So it can go up to 32 APSK type of data, very high modulation. So the group delay can actually increase the delay of the signal and will cause the so-called EVM issue, right? The error vector issue with for that particular signal, right? So we need to make sure that the bandpass filter have a very good performance, but the frequency range here is based on the planning. So it's chicken and egg. You want to plan first and then find the filter, or you want to find the filter first that in the market that can meet the frequency range, then go to the frequency planning, right? So it's quite tricky here, right? So what we can do is that we can do a lab simulation for 5G and the satellite service coexistence in C-band. So we have the gut band and bandpass filter mitigation. The mitigation can be measured and characterized in lab. There are 3 stages of lab test. First stage is to measure the performance of the selected bandpass filter. So we can look in the market, right? What are the models that is already in market? For example, microwave filter company, Asiasat, Nosat, all those are the brands that can provide the filter. So we look into the website, find the bandpass filter that is available, right? Then stage 2 is to measure the effect of bandpass filter where there is no 5G. We get the baseline first. And then stage 3 is to measure the performance of the mitigation that we deploy. So then we put the bandpass filter, we put 5G, turn on 5G, and we see how small the gut band we can go before we start to see the degradation in the signal, right? So if you're wondering, in Malaysia, this is a real picture in Malaysia. So this is a FSS receiver dish on top of a petrol station in Langkawi. So this is a feed horn, right? This is a satellite dish. This is where we put the bandpass filter, right? And this is the LNB. Okay, so the full receiver system here can be simulated in the lab, right? The signal, the 5G signal can be simulated by a signal generator, vector signal generator. And a DVB-S2 satellite video signal can be generated by either the vector signal generator or a dedicated broadcast generator, right? So we can simulate this. And what are the equipment required, right? So for this lab test, we need basically 4 equipment, right? The main one. The first is a vector network analyzer, like this ZNB8 here, right? This is to measure the characteristic of the bandpass filter, right? To get the parameter, group delay. The second will be the SMW200 vector signal generator. This is important because we want to transmit 5G signal, right? To simulate at a certain, a different power level, and a different power level that we can vary in the signal analyzer will determine the distance, right? From where the 5G base station and the satellite service receiver. It can also be able to generate a DVB S2 predefined signal, not real time but predefined. So basically, you can have one 5G and one DVB S2 signal here, right? Then we need a broadcast test center, right? The reason why we need this equipment because we want to generate real-time DVB-S2 signal at C-band. So this is a satellite service. I want to generate to simulate the satellite service, and this is real-time. So we can change the modulation setting of the signal to measure the effect of the filter group delay. So if we want to change from, for example, 8 BPSK to 16 APSK or 32 APSK, we can do it on the fly, so that we can see if the filter, the bandpass filter group delay has effect or not towards the signal. Okay, and of course we need the signal analyzer. We want to see whether the signal coming in has degrade or not. What is EVM value, right? What is the spectrum level now after we put in both 5G and satellite service together, right? And we need to see the modulation response of both the 5G and the DVB-S2, right? Or the satellite service here. Okay. So the first setup is to measure the bandpass filter performance. So basically, you have a filter here, right? The bandpass filter, and for that we want a prototype bandpass filter that we can test. So we measure it, and we want to see this is S21, right? We want to see first the insertion loss at the pass band where we want the satellite signal to go through, and then we want to see the suppression level, right? Well, at least 60 dB of suppression at the frequency that we want to reject the 5G signal. Okay, and of course there is a group delay that we need to measure as well, right? So this equipment ZMB8 can be used to measure the performance of the bandpass filter, especially if there is an interested party that want to design a custom bandpass filter, right? There is an opportunity for university to work on the a custom bandpass filter, because right now, as you know, we are not clear on which is the frequency range that is going to be assigned for. We know it's going to be 3.5, but how much of 3.5? 3.4 to where, right? And what is a gut band? And what is remain for the satellite service? We know it's up to 4.2 gigahertz, but start from where? So, this is a real life problem that, the academic can help to find the solution, right? Okay, the second setup is to simulate the bandpass filter at RF frequency. So we simulate at C-band first, right? At 3.5 gig, right? So we have the broadcast generator and the 5G signal generator comes in, and we measure it, right, with a signal analyzer. Okay, this is the second setup. The third setup is that we want to measure the bandpass performance at IF, means after the LNB. This is a critical part, right? So we have the equipment here, right? Again, mine goes to the bandpass filter, and we put in the LNB. Right? Of course, when you put LNB, you need to power it up, right? And you need to have a multiplexer so that you can measure the performance at the IF. This is important because you want to the decoder of the satellite service is reading the signal at IF. So the LNB needs to convert the signal from RF to IF, and it has to be clean, right? No degradation due to interference. So we can check the performance here. Okay. So let's go to some example that we have done for Malaysia, right? So bandpass filter measurement for 5G and FSS study. We have measured a few filters, actually more than this, but I have 6 in the slide now, right? For example, here from ASESAT, this is the model. Okay, microwave filter company, Frontier, ASESAT, and microwave filter company. So 6 model of filter, right? And so I have come up with a summary, right? In terms of this is the filter that is on the market, right? That you can buy off the shelf. So it's already available. So I have summarized it. So this is the filter model. This is the frequency range. For example, 3.6 or 3.65. We don't know yet, right? But we want to see the performance of the filter, whether it can do a rejection or not. So based on this measurement that I did, right, for the study, this filter, for example, I can say that it can be used as 100 megahertz guard band mitigation. Okay, this filter can be used as 50 megahertz mitigation, right, based on the value that we measure for the suppression level, for example, right. Another filter for like this one, we cannot, right? We see that the suppression is very bad, okay, very bad. And for this filter, this is very good. ASESAT BPF 370T, we can go up to 50 megahertz of guard band, right? And then there's another filter, 11383 from microwave filter company. This not suitable at all. So we need, you can see that I'm using the network analyzer to do the filtering of the bandpass filter, right? So that we don't want to go to the field and don't know which filter can be used. So then we have to, it takes a lot of time, many hours to set up in the field, right? So it's better to bring a filter that we have confidence for it to work, rather than to bring everything and then do the installation, de-installation that will take many hours of work. So in the lab, it is faster, and it can help to effectively reduce the workload when testing with the bandpass filter, right? For the example of the measurement photo, right? I also have export this into S2P file to be used in the software-based CAD if you want to do the optimization or design of the bandpass filter, right? But these are the result. So we have T700S. So some filter are very good, some are not. Some has some resonance here, so we can look at the result and we can tabulate out, right? So one of the best filter is the BPF T700T. You can see that it has a very good insertion loss at passband, less than 1 dB, and a very high suppression, 54 dB at 3.6 and 3.65 gigahertz. So we can go up to 3.65 gigahertz based on this measurement alone, right? So we are theoretically 50 megahertz guard band is sufficient. We don't need to go up to 100 megahertz guard band, right? So this is the summary of what we can get from the measurement using the network analyzer for the base for the bandpass filter. And we can also see the delay, right? The group delay, which is very important for us to know whether we can go with a high level or high modulation signal or not, right? So this is the group delay, right? So summary from the filter measurement based on the filter that we have tested of the 6 filter, we say that BPF 370 and 13961 can be used as 100 megahertz guard band. It is good, but only for 100 megahertz guard band. Whereas the BPF 3703 from ASESAT can be used for both 50 megahertz and 100 megahertz guard band scenario. Means here we can push the guard band to be narrower to 50 megahertz. So we save 50 meg of spectrum, because guard band means it's unused spectrum. It has been used as a separation, right? So if we reduce it from 100 meg to 50 meg, then we can make use of this 50 meg for to use by 5G, for example, or for the satellite service. Right? It's not a waste. So this is important of doing the lab test, right? To optimize the scenarios. Okay. And we found out that the other filter, these 3 filters are not recommended for the field test. Right? So from the 6 filter that comes to me for checking, I after measurement and only approve 3 of them. The other 3, I'll tell to the team that going to do the field test, please don't use this because it is not suitable for the range of frequency band that we want to test. Let's say from 3.4 to 3.6 of 5G spectrum. Okay. So this is what we need for the the first one I discussed is on the measurement of the bandpass filter. Now let's measure at the RF and IF scenarios where we put in the filter and we simulate the signal. Right? So what we need is first we need an LNB. This is an LNB that I use for my lab. It's not to say that this is the best LNB or what, but this is what I use for my test. I'm using a FIPA so-called a bandpass filter, right? The model is FieldSat. Model name, but this bandpass filter has a pass band at 3.7 to 4.2 gigahertz. Right? For the LNB, the RF is the input is 3.4 to 4.2 coming in, and output is 950 to 750 megahertz, 1.75 megahertz. 1.75 gigahertz. The gain is about 55 dB. Okay, we need a power supply, RNS NG100, and also other accessories, which are very important. The accessories will determine the accuracy of the scenarios. Right, we need the waveguide, frequency adapter, combiner, and other accessories. Okay. So this is the lab photo, right? So we have the signal generator. This is a signal analyzer. Okay, 2 signal coming in, one for 5G and one for the satellite service. Right, goes to the filter, right, and then we can check the signal, right? The signal coming in from out of the LNB, right? So we have this is 5G, right? And this is DVB-S2 signal for port 2, right? We have combiner, bandpass filter, bonus block, right? Power supply, okay? DC power to bias LNB. So these are the equipment and component that we need for the lab test, right? Okay. So test scenario, right? The first test scenario, what we can do is 5G we set from 3.55 to 3.65, so 100 megahertz of bandwidth for 5G. DVS2 3.71 to 3.73 means that 20 meg of channel, right? And then we have DVS2 IF frequency at 1.40 gigahertz. This is based on the LNB. And we test for 50 megahertz cut band. Right? So this is the setup. And we try to get the result for without the filter first, to get a baseline, and with the filter. Okay? So this is without the filter, this is with the filter. Okay. And we measure what we measure, the IF EVM level and also the DBS2 spectrum level. So this is a test result. Okay, this is without 5G. Without 5G, the initial EVM is about 3%. Right, no distortion at IF spectrum. So this is IF. This is a video coming into the LNB converted, and you see very nice spectrum. Constellation diagram is good, right? So this is without 5G, right? We did not turn on 5G from the signal generator yet. Okay. Then we turn on 5G without the bandpass filter. You can see the difference, right? The signal in the spectrum got distorted. Constellation is everywhere, right? It's no longer focused at the right right key, right? You're looking at EVM, error vector magnitude, from 3% to 31%. Okay? So this is a visible distortion that you can see from the lab test. So if let's say you design your own bandpass filter, if you want to know how good your bandpass filter is, you need to test in this scenario. Then only you can see whether it can pass the scenario or not. And it is very frequency dependent. Now, we put the mitigation, right? We're talking about, there are two mitigation here. About 50 megahertz got band and the bandpass filter. And you can see that the constellation diagram is good, right? EVM decreased from 30 to 4.65, close to the original EVM. And there's no longer visible distortion at the IF spectrum. Okay, so it means that the bandpass filter works, right? Example. Okay, so this is a sample measurement method that I want to show, right? Of course, we have to look into the detail of what are the power level or what is the frequency range. That can be flexible because we are using signal generators and signalizers. The one that is not flexible is the filter, right? So for the party that who did want to design the filter, it has to be fixed on that frequency. Okay, this is the test summary. So we test a few more scenarios, right? So we have TPSK, 8 PSK, and 32 PSK, right? Okay, without 5G is good. This is our baseline. But when we put 5G signal together, we pump in 5G signal without filter, we have distortion and we have high EVM. But if we put the bandpass filter in between the signal and the LNB, you have no more distortion and you have a very good EVM. Okay. Then we try to increase the DBBS2 modulation from QPSK to 8 PSK. Then we see that without 5G is 2%, right? Then we put the 5G signal, then we see interference. But with the bandpass filter, you see that there's no interference. The thing here is that when we put the 5G base station to the DBBS2 with the 8 PSK signal, right? It has interference, but the EVM is still there. Right? It's still good. But when you put the filter, it got degraded. This is the due to the group delay that I mentioned just now, right? And at 32 APSK, right? We try it with 5G and bandpass filter. You can see that it increased even further, right, to 5.3. So we have to be very careful. If the signal is at a higher modulation, then it is very critical, right? So what I want to conclude here is that we can do a coexistence scenario in the lab. Right? So if we want to plan for the frequency range, which is the problem right now, and also to plan for the cut band size and what is the suitable filter to be used. Right? We need to have this activity where we do a pre-study with the lab. Right? Otherwise, if you go straight to the field, and what I see with my own experience, that it will not give you a conclusive result. You need to have a proper lab scenario before you go to the field. And it is also very important if you want to do a design of the bandpass filter. Okay, there is an example here being done by my colleague in Indonesia, right? Or the RNS also involved with the regulator there, with the Indonesian regulator to do some testing, right? We have using the same equipment, but they add apart from measuring the signal with the signal analyzer, they are also using a Promax TV analyzer, right? So we can see that if there is an issue with the video, right? So based on our the study, right, what we see that okay, if there is 5G signal, right, without filter, right, and okay, this is no 5G. With 5G at -55, right, you can only transmit the signal at about -70 dBm. If higher than that, then there is no, you see, there is no signal. Okay, it failed. So this is the limit, -70. But if you add a bandpass filter, you can actually get the improvement up to minus 55 dBm. Meaning that the bandpass filter add the immunity to the receiver system for higher 5G power to go in. That means that when you talk about higher 5G power, means the closer it can go in terms of the physical distance. Okay. Okay. Once we done the lab test, we can go to the theoretical test or the analytical test. All right, analytical model. Okay. So over here, right, for us to do analytical model, we need to understand the scenario where we have the 5G base station. We assume at 30 meter, right, and then we have the satellite antenna. Right. The max gain, the main loop is the one that facing the satellite, and that is about we are looking at between 40 to 77 degree of angle, right? Or you know, what is the angle of the satellite dish facing the sky, right? So what we want here, we want this line here, right? We need to calculate the power that directly from this line. So we need to do a few trigonometry, right? We need to use the tangent, arctangent, right, to calculate the distance here. Okay, this we fix the height of the base station at 30 meter, right, and the height of the FSS antenna at 5 meter, right. We fix the height, we vary the distance, right, and we make some other assumption. For example, the power, the bandwidth that the 5G operate is at 100 megahertz, transmit at 200 watt. And this is the antenna gain of the 5G base station. And also we make some assumption on the satellite receiver, right? The antenna gain, what is the feeder loss, right? 1 dB, and also we put in the minus 60 receiver max input level signal, right? So we need to have a few assumptions, but what we want to know is we want to know the distance, the minimum distance for coexistence. Remember, we want to find the coexistence scenario. What is the gut band? What is the bandpass filter required? The model, the specification, and also the minimum distance. Okay, how close the base station needs to be with the satellite receiver, right? Or before it start to degrade, right? So we made some study and calculation in Matlab. So we have the 4 type of result here. First is same antenna height, blocking level without filter. Same antenna height, blocking level with filter. Different antenna height, blocking level without filter, and different antenna height, blocking level with filter. And we are able to do the simulation because one of the assumptions is that we took the 55 dB suppression level of the bandpass filter that we get from the lab test. That's why we do a lab test first. Then only we go for the analytical model. Right, then we can see here that okay, this is the baseline, right? The path loss of equal antenna and different antenna. So this is a baseline of the path loss. So this is the result. Okay, so if we're talking about equal antenna height, the separation needed is about 7.5 kilometer. This is in meter, right? But if we put in the bandpass filter, right, we reduce it to 13.24 meter based on the simulation by Matlab here. But this is same antenna height between the 5G and FSS. Normally it's different, right? We have 5G at 30 meter and 5 meter for the FSS. So we make a simulation again. Without the filter, again, it's about 7.4 kilometer. Means that you need to have very long separation distance. Imagine between each petrol station, you need to have 7.5 kilometer around that of distance, of safe distance where you cannot have 5G base station. So it's hard to get a very good coverage to the population, right? Because petrol stations are everywhere, right? So you need to reduce this as close as possible. So we take the data from the lab test, especially on the suppression level of the bandpass filter, right? And we put into calculation, simulate in Matlab. We found out that based on simulation, the separation distance is about 20.5 meter. Right. So every base station, at every petrol station near the point of the satellite receiver, you need only 20 or 21 meter of safe distance, right? Apart from that, you can have 5G already, or you can have the 5G base station already, right? So it's better in terms of the coverage, right? For this scenario. Okay, we have also went for a field test. Okay, for a field test in UTM. So this is I would like to review what we have done. So you can see here from the Google Earth map here, the 5G base station is here. It's located here. Okay, right, transmitting downward at about 50 meter from the ground level, and this is where we plan to put the so-called satellite service receiver, right? And this is the 5G parameters. We just transmit from 3.4 to 3.6 only at a time. Yes, this is the carriers. Supported range of the base station is this, but we only test up to 3.4 up to 3.65. Right. This is the antenna gain, the power, right? All the information here, and we do the test. Okay. So we have a few satellite receiver that point to different satellite. For example, one go to MESAT, Epstar 9, ASESAT 9, Intelsat 33E, right? So we have a few models, and these are the antenna so-called diameter, right? And we have 5G transmitting from here. Right? So 3 location of the satellite receiver. So we have done some test metrics, and we do a test on different types of donors block and so on. Then we can come up with some result here, right? The rejection and so on. So this is the test. So this is the dish here and the dish. Okay, this is the TV analyzer that they use. Important equipment that they are using here is also the spectrum, the portable spectrum analyzer, where you can see the distortion here, right? And we also have a SNG unit coming, but we did not have enough time to do the test with the SNG. It's mostly on the fixed station here. Okay. So what we see here, this is an example of the scenario. Okay, example. There's a lot more of this data, but I want to show you what the equipment can do to help visualize the issue. For example, here, right? When I turn off the 5G, right, I have very good so-called IF signal from the satellite, right? This is IF 1.5, right? This is 1 gigahertz span at the IF. Here we focus at 10 megahertz span of the IF, so we can see very good signal, right? Very clear. We put the filter, one of the filter, I will not name it here, and then we set a 100 megahertz cut band. Means that the 5G base station transmit up to 3.6 only, right? And then the signal from the satellite is transmitting from 3.7. We can see here there is 5G. In the wideband measurement, right? You can see there is 5G signal here, but it does not interfere yet the signal that we want to see, the intended signal. Okay, so right, this is the separation that is required, right? Now, if we reduce the guide band, right, from 100 megahertz to 50 megahertz with the same band pass filter, we see the degradation. Right? So this is fair. So this is a sample of analysis that we can do when we do the field test using the portable spectrum analyzer. So the analysis that we have come out from the field test, but it's not really 100% conclusive from the last field test we do. But the general conclusion is that the VSAT will experience blocking interference when LMB is unable to fully reject or reduce 5G signal below the satellite reception level. The level of LMB blocking interference reduce exponentially at higher VSAT downlink frequency. Of course, you push the spectrum of the allocated spectrum for the FSS higher, then you don't see you will see less of the interference. But this, we want to see what is the closest performance, right? I mean the closer signal. And also, no significant impact is observed for both direct and indirect facing VSAT at distance of 85 meter and above. And no interference was observed with 100 MHz guideband. Means that, okay, 100 MHz guideband somewhat will work, right? We're talking about 85 meter and 100 MHz guideband. You can see from this is the analysis from the team that I can, so you can look at it, and there is a scenario already. Whether you accept the scenario or not is another question, right? 100 MHz guideband with that filter, whichever that they are tested, and a distance of 85 meter. Good? Not good? Right? This is quite distant, but it depends, right? By the regulator, by the operator, by the stakeholders, whether this separation distance is accepted or not. But I think the more critical issue is on the 100 MHz guideband. Right? So I would like to propose a future field test where we will have more information and easier. I don't think that we need to have this huge so-called satellite civil receiver. Maybe we can find a smaller one that we can attach to a truck, right? Maybe a 1 meter diameter. Then we can do the calculation, especially from university. Maybe we can do the calculation to compensate the difference of the diameter, right? Then we do a test, okay, with a truck. So then we can have multiple result on the pass-fail in terms of the distance, right? And the equipment that we can use is, of course, the first is a handheld spectrometer that we use in the previous field test. We should also use the 5G UE, Qualipop, RNS Qualipop UE that can focus the beam. So we want to look for worst case scenario. Remember, in 5G, right, you have the broadcast, the SSB beam, and also the data beam. The data beam will only transmit if there is data, right? There is a data request, okay? The SSB beam or the broadcast beam, which is transmit all the time, is about 3 dB less in terms of power compared to data beam. So if you want to go for worst case scenario, then we need to have the UE here, right? So that the beam is focusing, one of the beam here, the data beam will be focused to the satellite dish here, right? Because the phone will be beside it to simulate a even worst case scenario, right? Then you can have a scanner, TSMAC scanner, right? Of all the equipment here, I think this is the very important equipment that can be utilized to analyze further the scenario, the collision scenario, because we can record the spectrum, right, while the car is moving, right? The truck is moving. Then we can see the changes in the degradation on the fly, and as well as the scanner, this RF receiver, right, can decode the 5G signal that's coming in and to see whether you are still getting a proper 5G signal or not. Right, so this is the equipment that I would like to propose for future field test to get a conclusive measurement result. All right. Okay, so this is apart from that, we can also do a 5G performance and coverage test at the same time while doing the coexistence test, right? So we need the Qualipop UE, right, for the data throughput, focus the SSB beam toward the receiver, and also for the spectrum measurement, the 5G decode measurement, right? The coverage measurement, you need to have a receiver, right, like this TSMC. Let's see what I'm doing here, doing the measurement, right? but we also need a truck that can drive and vary the distance to have a more conclusive analysis. Okay, this is my proposal, and in my opinion, should be a very good way of doing the field test if we want to really resolve the coexistence issue. Okay, let's look at the case study in Hong Kong. What have been done, right? So in Hong Kong, they segregate the frequency, right? Again, like what we planned. So the 5G has been allocated from 3.4 to 3.6, and then there is 100 megahertz guard band, okay, with the filter specification that is can support this, and the remain 3.7 to 4.2 gig rest with FSS. So this is a SMATV system. So we have the dish, the feed horn, then we put the bandpass filter here, the LMB, right? So this is the field test. Apart from here, we also done the simulation, calculation, and also lab test in Hong Kong, right? So based on the study, it seems that the authority can finalize the scenario and ensure the harmonious coexistence between these two services, right? It has, so what I want to highlight here, right? We have a case study in Hong Kong, and it sort of working, right? There's 5G is alive in Hong Kong, and it's already there, right? And the satellite service is also still transmitting at the C-band, right? Still operating at the C-band. So we have a reference that the two services can live harmoniously with each other, right? But we need to do the test, right? So that's why I'm proposing this test, so that we can achieve or resolve this coexistence issue, so that the both 5G and the satellite service can coexist harmoniously. Okay, I come to the end of my presentation. If you need to download the slide, you can scan here, or you can go to this site. Please help to fill in the feedback form for me as well, for my use. Okay, and now it's a question answer, Prof. Fauziah. So thank you everyone for listening to my presentation just now. So now, if you have any question, you can ask me. Thank you.
Okay, thank you, Mr. Anwar. So basically, there's a few questions dropped in the chat box. The first one is from Yoharaj. Why there is a need to down convert satellite signal to IF in the LNB?
Why is there need to convert the satellite signal to IF in the LNB? Converting signal to IF is a standard procedure. Even our radio, right? Our radio is we call it a super heterodyne radio, right? So RF signal come in, convert to intermediate frequency, right? So this is an issue for many decades already. Why do we need to convert to IF? Right? The spectrum analyzer is also super heterodyne. Signal coming in, what we see is IF. Now, the issue of direct conversion means that you receive RF and convert it to the data directly, to the visual data or the audio data directly. If you go and study about it, it's because there is a DC offset component in that RF that can deteriorate. That's why we, or the past engineer, do a conversion so that we want to remove the DC offset, right? Although nowadays, when we come to the modern age, there's a lot of IC that I know that try to compensate for this DC offset, but in cost wise and complexity, it's still, I don't know whether it's feasible or not. So the easiest way to remove the DC offset issue, right, and also the more practical way is to do the IF. Everything is changed to RF, even our radio, our TV signal. So this is common practice. Unless we can resolve this DC offset issue to do a direct conversion. Okay. Next, where can I download the PDF files? You can download it here. and also fill in the feedback form. Next question, Prof. Apa ya?
Yes, okay. From the same person, Yuharaj, as the government will build 5G network to drive special purpose vehicles, is there any discussion or agreement in determining the size of guard band or type of band pass filter in the C-band to be used with the government?
This one answer the question.
Yes.
Yes, this is okay. I understand the concern from Mr. Yoharaj, and I actually share his concern. And this, I think, this is what we want. We want to have a discussion on this, but I don't know what's the current status right now in terms of the policy. So I cannot answer this question. This is a question to the government, to the regulator. But I share the concern from Yoharaj as well. I do want to see if they can have an open discussion or some agreement in terms of this guard band. Thank you.
Okay, I think that's all. The question from the chat box. Any other participant? Maybe you can actually ask the questions by turning on your mic. Okay.
Assalamualaikum.
Waalaikumsalam.
Yeah. I'm from UTM.
Prof. Apa khabar?
Alhamdulillah. Yeah. No, just I'm wondering, is there, I mean, in terms of mitigation techniques, you say that there is a lot of other techniques as well besides band pass filter. Have they done this technique as well, besides using the band pass filtering?
Not in wait, let me find this.
Because there is a lot of mitigation. Yeah.
Not in a proper way lah. In terms of the study. You know, people test one place one time. You know, okay, we check it. But there's not a proper study.
I see, because number 4, they say they optimize the 5G base station to reduce antenna gain in the interference direction. What does it mean, this one?
Okay, means that, for example, I'll give you a real case example. We have satellite in receiver, big satellite receiver for TTNC in Cyberjaya and Bukit Jalil, right? Okay, so for that frequency, it's not adjacent. When we want to do segregation, it's adjacent, right? But it's a case where it will be co-channel, means that the 5G signal and the TTNC signal would be same frequency. So here we need to optimize the antenna direction, because you cannot put the filter at the TTNC big.
I see, okay.
Right? So we can do this optimization, means that planning of the pointing of the antenna so that it won't go to each other. If there is 1 or 2 cases, right? You cannot do for a ubiquitous environment. That is, for all the petrol station, you cannot. It's not possible, right? So that is why we have to look at some of this mitigation is suitable for a certain scenario. So that's how we do it lah.
Okay, right. Thank you.
Right. And one more thing, Prof. If you look at number 7, right, add a physical isolation, caging. This is where I think the academic can make use of the 3D simulator. I'm not sure if there is such a thing where you can design the Faraday cage. You know, because it's hard in the field if I want to know or identify what is the right isolation, the right size of Faraday cage. You know, so this is something that not really have been done before. I believe in terms of the proper study. Yeah.
Mr. Anwar, when you're talking about physical isolations, is it refer to something like a radom ke yang dia boleh somehow allow specific signals to go in or penetrate?
No, physical isolation is something like, okay, so you it's not just caging, it's not just Faraday cage. Okay, let's say you have this all antenna, right? Maybe you can put 3 in a pot at the back that you can actually somehow prevent a physical, you know, direct line of sight between the antenna and between the satellite service antenna and the 5G antenna. So because we see there is some tests that if we put tree in a pot and behind the receiver, it seems that it can help a bit, but we don't really understand the physics of it. We know that we can put a physical isolation, means that it's either fiber cage, apply in a pot or something. That's why I mentioned that by physical isolation.
Okay, understand.
Yeah.
Okay, one more question, Azza. For 5G C-band TDD, how 5G UE can interfere FSS? Is there any study on it?
Sorry, what's the for 5G C-band TDD?
How 5G UE, the equipment, the device, maybe the mobile for 5G can interfere the FSS? Because you're actually talking about base station, 5G base stations, right? But how about in the perspective of UE, 5G UE, user equipment?
That's a good question. Okay. In 2019, there is a meeting in APT, APT meeting in Jakarta. They did mention about this. I think there's a study by Qualcomm that says that yes, the 5G UE, right? You have a 5G UE, right, near the satellite. When it doing uplink, right, it can interfere with the 5G base station, correct? But it is not worth to study on that particular issue because the interference from the 5G downlink will overlap. For 5G is about 23 dBm, correct? Maximum power. From the base station, 200 watts, right? 53 dBm, right? So before the UE can interfere with the satellite, it's already being interfered by the base station. That's why the study is all on the base station. The base station interference overwhelm the satellite receiver. But there is a case where a colleague of mine in Indonesia is doing is that maybe if you are at the back in some scenario, like you say in Indonesia, right, where the user is at the back of the 5G of the satellite receiver station, that even though the 5G signal is not there, somehow it still can interfere. So I'm not really sure about that, but it is something that maybe we can further study on it. But the previous argument is that because we want to focus resource and on quickly resolving the issue, right? So we focus on the base station first because that is more pressing in terms of the power that's being seen by the receiver. But if we have time and if they have the resource to do it, I think we should study this as well on difference of the 5G.
Okay, so question from Muhammad Amin. I'm not sure what he really meant to, what to do the mitigations. Maybe Muhammad Amin, you can rewrite your question again in the chat box. Okay, next, Azim Adnan, what you are looking for when choosing the best filter?
That's a good question. It's chicken and egg, right? We want to plan for the frequency and the cut band, but we want to make sure the filter can satisfy this condition, right? So either we look into the market first, right? And from the market, we see the performance, we test, and then we make the planning, or we set the plan and say, okay, whatever it is, we need to get the filter that can meet this spec. So, that's the dilemma, I would say. It's a bit of a paradox, right? But basically, what we're looking for is the pass band insertion loss at the frequency range, this is where we need to get the understanding and agreement with all parties. The stop band for both low end and high end, especially at low end where the 5G is going to be located, and also the group delay. So these are the parameters that we need to look at when we want to choose the best filter.
Okay, from Ola Kunle Elijah, have you published the finding of this research study in Malaysia? This, yeah.
What does he mean by publish?
I think the way that you should have you somehow submit as a journal or you have published it somewhere. Maybe he want to look into the details of about this research work and so on.
On my own, I think it's a bit difficult because I'm not really focused on that. But I can work with university partners, like anyone who wants to work together with me on this, then maybe we can publish. But at the moment, we don't have any formal publication yet.
Okay. So Muhammad Amin, who need to do the mitigations? The satellite service provider or the 5G service provider?
Okay, this again a question to be asked to a different party.
Okay, it's something to do with the government policy, isn't it?
Yes. Good question.
Okay, from Azad again, for my question, if OTSTDD, the uplink is the same frequency with the downlink, DL.
Yes. At 3.5, we're talking about the 3.5 gigahertz, it is TDD, right? So yes, the uplink is the same frequency. So there is theoretically, right, there can be an interference that can come from the UE as well. But like I mentioned, at the earlier stage of the study, people put this aside because they want to focus on the base station first. Because before the satellite receiver being interfered by the UE, it will be interfered by the so-called the base station first, right? Remember, when you have the UE, right, the UE, especially in the NSA environment, right, it will not be transmitting signal in the 5G, right? Of course, if SA is different case, right? It will transmit the data, the broadcast signal, right? When you try to search for the base station, it will be in 4G, right? It will be at the band 7 or band 3, band 1. So it's different frequency than the C-band. Only when it's connected to the 4G LTE layer and there is a 5G signal available at C-band, then only the base station will instruct the UE to change to the 3.5. But before that, means that there is a base station 3.5 gigahertz downlink available. So it's already interfered. Before the UE change from 4G to the 5G, it's already been interfered by the 5G base station if the signal is there available. If there is no 5G signal available and the UE is near the satellite receiver, then I believe there is no 3.5 gigahertz for NSA at least signal transmitting. It will be still in 4G. So I hope that I can answer Azhar question. We should study this after the government applies a 5G band. Yeah, sure. Or we should study first and advise on the 5G to finalize the 5G band. Is something that can be think about. Next.
Is there any more questions? I think there's no more question. But I think what you have done in terms of the field site testings, somehow it will give some conclusion for government to start to somehow maybe realign the government policies, things and so on lah. Maybe it can solve a few repeat questions that who actually supposed to in charge in terms of this kind of like mitigations. Okay, so I think that's all for today's session. Before we left, is it possible for us to have something like photo sessions? Okay, maybe all of you can turn on your video. Miss Anwar, you can somehow stop presenting, so actually I can have a complete. Okay, we're waiting for more participants volunteering to turn on their video.
Assalamualaikum, terima kasih Encik Anwar.
Waalaikumsalam. Terima kasih. Organize.
Alright, baru sampai rumah. Okay, sorry. Okay, carry on . Okay. Good.
Okay, ada lagi yang nak turn on? 1, 2, 3, 4 lagi kot. Sekejap Okay. 1, 2, 3. Smile. Okay. One more. Okay, 1, 2, 3. Smile. Okay, I think that's all. Thank you for today's session.
All right, thank you everyone. Assalamualaikum.
Salam. So all the attendance e-certificate will be given towards your email lah. So please make sure you fill in the attendance. Thank you guys. So the recording will be uploaded in our chapter YouTube later on for your reference. Okay.
All right, thank you. Bye.
Okay, bye.
Okay, thank
Bye
you, Anwar.
everyone.